and let's get rolling. So, today's topic, named Give Me a Fixed Point, is we will be dealing with how we display the result, how we get to the final results. So, where did we end it the last time? This is the calculation of uncertainty. Let us be reminded that we need to really distinguish what type of uncertainty we are looking at, and what gets most confused is the standard uncertainty, which is more or less a statistical parameter, and the expanded uncertainty, which is a multiple of it, and which is a parameter suitable for later interpretation. So what we've covered in the past webinars was how to get to the individual standard uncertainties. And we are all the way making the assumption that they are normally distributed, so that we can calculate the combined uncertainty as the square root of sum of squares. And that is the formulas displayed here. One for uncertainties connected with the measurement system. That's the blue one. And the red one for the measurement process. One of the assumptions needed in this formula is the mutual independency of these uncertainties. They should not be mutually correlated. And they mostly are not. But there is a specific case where we can expect this correlation, and that is the equipment variation. So that's the reason why there is this little trick in both of these formulas, that the equipment variation is taken in the measurement system as the maximum of repeatability on reference or resolution. In case the repeatability on reference is 0, let's say, it is usually because the resolution is too big and that the measuring device is not capable of distinguishing between the individual measurements. And the same trick here is in the measuring process, where we take the maximum of the two which already are in the measurement system, and we include the equipment variation on the actual object among those. So that's the trick for the apparent correlations. And we don't really, in this simplified calculation, we don't really care about other possible dependencies. The result then may be slightly bigger. This sum of squares takes them all independently, so if they are summed up, the result may be slightly bigger than compared to a case where we would account for that. Another trick worth noting is that the uncertainty of the measurement system comes down into this formula, which is saying, in other words, the measurement system uncertainty is one of the uncertainties of the measuring process. All right, so this is the standard uncertainty with the little u, and they are then being expanded to a number which we can actually use. There is a long time tradition to expand it to the level that the coverage probability is 95%. Why 95%? Nobody knows. That's a tradition. The only good thing about this is that it is not very disputed, and I have rarely seen a different coverage interval. So when there is an expanded uncertainty, you can be almost sure that it is twice the standard uncertainty, which makes things simple. Do we always need these 95%? Probably not. But we are in an industrial environment, so standardizing things makes our lives simpler. All right, the reason for the two is obvious from the normal distribution. And this basically says that the region of uncertainty, which is around the value that we have measured, the width of this is 4 times the standard uncertainty. That is this value, this region down here. Okay, so now we know how big it is. We can actually relate to that number. This number, the little u or the capital U, is in the units of the actual measured quantities. If we are measuring length, this is in millimeters, meters, kilometers. If we are measuring weight, this is in grams or kilograms or whatever. So we cannot really compare the measuring device to each other. We need a non-dimensional quantity to be able to say something about the measuring device in a more general terms. So this is the dimensional one. The uncertainty is the technical side of things. But if we want to generalize that, we need non-dimensional quantity. Usually these are called indices. So in this realm of industrial uncertainties, we have what's called the QMS and QMP, which is a quality index of the measuring system and the measuring process. And it is calculated as a fraction of the width of the uncertainty. So this up here is this region here. This equals the 4 times the standard uncertainty divided by something, divided by some reference interval, which is also in the units of the measured quantity. So what this something can be? Well, first of all, the specification limits lend themselves to step in. So the specification limits, that's quite easy. That's the upper specification limit minus the lower specification limit. Sorry, I have the check here. The D and H instead of L and U. So that's one side of things. And this is the most usual one. We usually know what are the specification limits of the parameter. We know it from the drawing. And the usual standards, particularly the VDA 5, the German standard, and the subsequent ISO standards are actually giving limits to these values. It is 15% for the measuring system and 30% for the measurement process. So the region of uncertainty of the measuring process can be up to approximately 1/3 of the tolerance limits. And this at the first sight seems rather big. Almost 1/3 of the tolerances is covered by the measurement limit. So it seems that there is very little region in the middle in which we actually know something about the measured object. And then there are quite a big span of regions of uncertainty. Well, that is true, but keep in mind that all what we are doing here and the capability that we in the end want to conclude on is driven by the idea of controlling the production process. And it is much easier to say what is the state of the production process from several measurements taken at control points and possibly making a control intervention than it is to say on one particular part whether it is within the tolerances. So the decision about one individual part being within the tolerances is more difficult than the decision about a production process being of such quality that there is a high probability all the outcomes will be within the tolerances. That is the reason is that with the process we are more or less dealing with averages, or generally speaking mean values, and the uncertainty of the mean values are smaller than the uncertainties of the individual values. So this 30%, be careful about that. The measuring device is okay for controlling the production process. When it comes down to individual decisions, the uncertainty needs to be kept in mind, and you can never tell whether it is too big or too small unless you know how close is the result of the measurement with respect to tolerances. When close to tolerances, there is nothing what can save us. We will always be within the uncertainty region. But when we are further away from the tolerance limits, either way, either in the conforming region or out of it, you can actually make a decision. The measurement system is half of that. The reason for this is to be able to make a decision about a measuring device which you don't have at hand. When you are intending to purchase a measuring device and you don't have the possibility to make experiments on your parts within your measuring process, it is a good practice to make sure that the measurement system uncertainty, which in the standard devices comes from the maximal permissible error, is not more than half of what you would expect from the total measuring devices. And that's pretty reasonable. There is no one good number which should be put there. Should it be 10 or 15 or 20? Well, suddenly it should be less than 30. But where this number should be, this is pretty arbitrary. So the standards are saying 15%. We respect that in Yarvin, but is that the best number? Probably not. So when it comes to measuring devices which you already have and which you are already studying, it may happen that the measurement system is over 15%, let's say 20, but the measuring process total, the Q and P, is less than 30%. Well, in that case, there the standards, the measuring device is not conforming. But I would say if the QMP is less than 30%, there is no reason why not to use that measuring device. The measuring process, whatever it is, whether you may have very good people working with that device, or your environment is clean and very suitable for that measurement, or just the measuring device is very robust with respect to the measurement processes. On the whole, the smaller error in the measurement process uncertainties gives more weight to the measurement system uncertainties. So in my opinion, the later one is more important. And if this is okay, I would say the whole process is okay. Well, there are two other ways of what we can relate to down here, which are actually a little older, and that's the process limits. That's this one. The reason for that is that we actually want this measuring device to be able to control the production process. So the idea about relating the device to the process limits is that we want to be able to shift the production within the variation the production actually shows. And I'll show in a second what I actually mean. And there is one more step beyond that. In cases we are not able to observe the process limits because maybe the production is not yet running. We are getting ready for that. So we can work with the expected process limits based on the desired process capability. So how it works. The process limits, the upper and lower process limits, are estimated to cover the 99.73% confidence bounds. That corresponds not +-2 standard deviations, but +-3 standard deviations. So there is a discrepancy between how we treat the production process and how we treat the measuring devices. This corresponds to CP indices of exactly 1. So if the measuring device is within 30%, the +-2 expanded deviations of the measuring device is within these 30% of this 99.73 interval, then it is okay. And then we can go to CPs of different sizes. We don't need to have CP equal to 1. Usually the CP is more than that. So if the CP is 2, we expect that this, let's say 2, we expect that the process will cover only 1/2 of the tolerance limit. So we are somewhere in the middle. There is still way down to the specification limits, and we allow the measuring device to cover only the 30% of this region in the middle. So that's how the CP is used to calculate the criteria for the QMP. So going the first way, that's the tolerances. You need to know the tolerances. Going the last way, you also need the tolerances and the capability in this. The second way, with the process limits, needs the actual production. But note that in this second way, we don't have the specification limits. All right. I will now hand over to Martin, who will show you how this is being done in Yarvin.
Jaroslav, can you please give me the screen share?
Oh, sorry.
It's writing is disabled.
Yes, please go ahead now. It should work now.
Yes. So in Yarvin, we have the first thing you have to choose, if we start from the beginning of the validation act, how the steps is going. The first thing is to select the reference intervals. That's what Jaroslav was speaking about right now. You have those three possibilities: specification limits, process limits, and process capabilities. If you are loading the data with DFQ files, the specification limits will be overtaken with the nature limit, if it's in this case. Or if you want to use process capabilities or process limits, it has to be filled in manually, because it's something different, and we assume that you know what you are doing, so it's necessary to put it here manually. And according what reference intervals is here selected, or where the values are filled in, this is then reflected in the evaluation. And if we go to the evaluation screen, the first you can notice that is something we call total result. In this case, it's not suitable, and this total result is the worst results from all characteristics. You can see we have some that are not capable. That's the reason why the total result is also, let's say, red. In this overview is the most important results from the Validation Act. You can see we have the QMS and QMP from the VDA 5 and ISO standards. You can have the uncertainties, and from the MSA we have gauge RNR and NDC. For the color coding, green and red, we use this only for the QMS and QNP. And the reason why it is only here is because in those standards, VDA 5 and ISO is said that QMS should be less than 15%, QMP should be less than 30%. In the MSA, you can find there some limits, but also you can find there that this is only general recommendations. So that's the reason why it's not here, the color coding. Sometimes it can happen that the total results will be yellow, conditionally capable or conditionally suitable, and that will be in the case that you have some result that is suitable only if you do the trend compensation. That's something that's suspicious. So that's the reason why we give you this information with this conditional suitable results. But this is only the automatic evaluation. In Yarwin, the final decision is up to user. So you need to know if the results you are getting is okay for you or not. And if you are okay with this, you can change the overall evaluation. You go for it is suitable and write some remark to be clear why do you change it. And this information is stored to the Validation Act, and it can be seen on the Validation Act's overview. I will show you this in a moment. If we go to the detail of some characteristics, the overview works as a filter. You can go, for example, the worst here, and you can see the uncertainties that is calculated. The size of the bubbles is proportional, so you can see what uncertainty is the biggest, what is the lowest. You can see if the uncertainty is type A, so it's calculated from the experiment, or it's type B, some other sources. And you have the results. The results are divided to measurement system and measurement process, and measurement process is divided to ISO or VDA or MSA 4. And for each characteristics, you have also the advanced or more details, where are the partial results. So here you can see what reference interval was used for this specific evaluation. In here, it's specification limit. You see that it's with trend compensation and the overall results. Not only the uncertainties, QMS, CG, CGK, but also with some averages, standard deviations, bias, and so on. Graphics with the reference interval, with the regression line, with the value of the master. For the measurement process, also more data is here. For example, here you can see the components that is used for gauge R and R evaluation, part evaluation, evaluation on object, and so on. And
all
also,
right. I'm sorry to step in. I think this is what we have time for today. We will need to leave the rest for the next time. The next time we'll finish this, certainly. We'll show you what are the priorities in these three possibilities for evaluation, how this is done. And next time we will also speak how this QMS and QMP relates to MSA results, the CG, CGK, and RNR, and how possibly we can set consistent evaluation criteria. And we have one question to respond to in the Q&A. The question is how the measurement, how the equipment variation is subtracted. It is a question from Ulf Stoiber. I hope I have the pronunciation right. So it is right here. This overall is the uncertainty from repeatability taken either from the resolution or repeatability on the reference or repeatability on the object. So the measurement system gets subtracted from the maximum done on the measurement process. So I hope we have responded to that. We are a little bit over time. If there are more questions, please write us an email and we'll do our best to respond next time. For today, thank you very much, and I'm very much looking forward to seeing you next month.
We are here to make you smart. Deribet, we are deribet. Deribet, we are deribet. Deribet, we are deribet. We are deribet.